Okay, we can start.
Okay,
Thanks.
so we have stated our goal, which is Gabriel's theorem, which I have written over here. So the quiver is absolutely any quiver. Okay. So for quite a bit that we will do today, Q is allowed to have cycles, loops at any vertices, anything whatsoever. Okay. So that's what is given. But these three things are equivalent. So Q is a finite type. That means that it has only finitely many indecomposables. So remember, our goal was to try to study indecomposables. Uh, and then the claim is that this is equivalent to the quadratic form of the quiver being positive definite, which I have recalled below, and which is really the same as being the underlying undirected graph of Q is of type AD, A, D, or E. And I wrote down those pictures yesterday. So this is going to be our goal, which we will almost reach today by the end, or rather, will be able to grapple with a large part of it by the end of today. So okay, so the action for almost the entire lecture and maybe the entire lecture is not going to be on representations at all. We are going to look only at number 2 and number 3 in here and try to show equivalence of that and then go beyond that. Okay. So that's what our goal is. First, prove the equivalence of 2 and 3. Which means we have to see what the quadratic form of the quiver is. And so for this, what I do is I just sort of make a new beginning, because you see, there are no representations over here in number 2 and 3. So I take any undirected graph. I call its vertices 1 through n. So the number of edges connecting I and J is the same as Nij or Nji. And as I've written over here, loops are also okay. So recall what the quadratic form is. The quadratic form is I take the sum of x. So x is a vector in z to the n, right? So I'm working um, in this pre-abelian group of rank n. N is the number of vertices. So for any vector x1 up to xn, I simply add the squares of the entries, and then I subtract uh, product of xi xj for every edge. And since there are Nij edges between I and j, I have simply taken this sum over all pairs I and j. Notice that I equal to j is allowed over here. Okay, so this is the slightly more general thing compared to yesterday. But the proof that I sketched, which I have written below again, is really stays the same. So let's go through it. Right. So remember that there is an associated bilinear form that is just given by this formula. So if you work this out, then you get the following formula. So what is different compared to yesterday? I'm simply allowing this NII. All right. So what has happened? Uh, if you just, this is a matter of just plugging in. So if I take x plus y, then I will get xi plus yi the whole square minus xi square minus yi square. And therefore you will have this 2 times xi yi. But the term corresponding to I equal to j from the second summation that I have pulled in the first one. That's the reason for this minus nii. And here the index now is from I not equal to j. This is a matter of just algebra. The reason why this I less than j changed to I equal to j is that you see that when I expand the parentheses, I will get a sum which is xi yj plus xjyi. So that's the reason. This is simple algebra. So looking at the formula for this bilinear form, I can write down its matrix. So remember that alphas are just standard basis. So alpha 1 is just 1, 0, 0, 0, and so on. So I can read off from this formula the matrix of this bilinear form, and which is going to be, if I is equal to j, then I simply get uh, 2 minus nii, which is coming from here. And otherwise, I get this minus of nij as the entry that records what the value of the bilinear form is on each pair of basis vectors. Okay. So this is going to be my bilinear form or quadratic form associated to the given quiver, but really this gadget doesn't depend on the arrows at all. So I'm looking at the undirected graph. All right. So the bilinear form is defined from the quadratic form, but remember that that from the bilinear form I can get back to the quadratic form just by evaluating the bilinear form on x and then dividing by 2. Okay. So I call cube or the associated bilinear form positive definite. It means that q of on any non-zero vector is strictly positive, and semi-definite if it is greater than or equal to 0. Okay, so a couple of definitions that we are going to So remember what our goal is. I want to show that q is positive definite precisely when the quiver is of type ADE, and for that we are going to take the help of the positive semi-definite case by showing that the form is positive semi-definite if you have either ADE or the corresponding Euclidean diagrams with the tildes. Okay. For that, a little bit of terminology before we state the theorem. So the radical of the form is all those vectors such that z such that when I evaluate the bilinear form on any other vector, it gives me identically 0. So if you are thinking in terms of perpendicularity, which is not a bad way to go, okay? And it is exactly right if the form is positive definite, then we are saying that the radical of the form is those vectors that are perpendicular to everything. Okay. A little bit of terminology. I'm going to define a partial order. I call a vector x greater than or equal to vector I if it's slot-wise bigger. So that just simply means that the xi entry is bigger than the yi entry. Okay. Yeah, and I'm following this terminology. We call the vector x sincere uh, if if every slot is non-zero. I've never seen this used anywhere else, but in my reference, this is what he says. So I'm simply following the terminology. Okay. All right. So our first goal is to classify graphs with positive definite and positive semi-definite thing. Okay. So let me first show you the theorem. So this is the theorem that we are going to do. Okay. So if the graph is of Dynkin type, that is AD, then the form is positive definite. Otherwise, if the graph is Euclidean, that means the corresponding things with tildes, then Q is positive semi-definite, but not positive definite of 1. All of these are claims that we will prove. And moreover, we can in fact tell exactly what the radical of the form is. It is all integer multiples of this special vector D that I wrote down yesterday in the diagrams. Okay. But if this is not the case, then the form is not positive semi-definite, and so that means that I will always be able to, for all other quivers, for all other graphs Q, I will be able to find a vector whose non-zero vector. In fact, there is a vector greater than or equal to 0, a positive vector I will be able to find such that Q of x is less than 0. Okay. All right. So how are we going to prove this theorem? We are going to prove this theorem by means of this key lemma. So I had written this lemma yesterday, and it is exactly the same thing, just with slight additions. So one is that, so see the assumptions. I'm given a graph, and I'm assuming that there is a very special vector D given. With what properties? The vector is non-zero, and it is a radical vector. That means that this vector D is assumed to be perpendicular to everything, including itself. And this is the hypothesis that I missed writing in the statement, but then we came up against it in the proof, that I do want this vector to be greater than or equal to 0. So remember, greater than or equal to 0 simply means that in every slot must be greater than or equal to 0. Okay. And because the vector is non-zero, which this means that at least in one slot it is strictly greater than 0, the entry. Okay. So under these assumptions, what do I get to say? I mean, the main thing is that this allows me to show that Q is positive semi-definite. Okay, so that is the key result. But in fact, we will see before that this forces this non-negative vector actually to be sincere. That means in each slot, it has to be greater than 0. Okay, this is a simple thing that we will prove right away. And moreover, we will be able to tell in the end precisely what the radical is. The radical of the form is going to be nothing more than multiples of this vector d, rational multiples of this vector d. Remember, I keep on saying vectors, but I'm really working over here in z to the n. Okay. Any questions so far? Please do stop me if there are any issues. See, the thing about writing the notes beforehand is that one can then tend to go quite quickly. So if something I'm not saying, if something I'm saying is not clear, please do stop me. All right. So our first job is to prove the first bullet point. Okay. And for that, I simply use the fact. So remember, D is a radical vector. That means it's a bilinear form with everything is zero. So in particular, I take the first basis vector. Now it's a matter of just reading the formula. Okay. So let's go and look at the formula. Uh, so instead of looking at this, let's just look at this, right? So one of the vectors is alpha I. In the second slot, I have some coefficient. So I just use linearity in one slot to see what I get. So this 2 minus nii will come in slot I, and in every other slot I will get nij, along with of course the respective coefficients that are in the vector xi. Sorry, in the given vector d. So d is radical, so this is 0, and I have just plugged in the formula. So for the slot I got the coefficient 2 minus nii times, of course, the scalar coming from D. And in the other slots, I got nij's coming with coefficients D sub j. But remember, this is 0. That means by assumption, because D is a radical vector. And that means that this expression is 0. Well, let's look. I want to show that the vector D is sincere, right? That is, in every slot it is non-zero. Okay, so let us suppose that in some slot it is 0. So fix some v, fix some I, and suppose it is 0. That means that this first term disappears, you see. And that means the second term must also be 0, which is what I've written over here. But now look here, all the terms that are in here, let's look at them. Nij is the number of edges, so that is always non-negative. Yeah. So, and this d sub j by assumption, which I had missed yesterday, is in every slot it is non-negative. So this is a sum of all non-negative terms. That means that every single term has to be 0. Okay, but remember that the graph is connected. That means that this vertex I is connected to something, and for such j's, nij is non-zero. That means d sub j has to be 0. So d sub j is 0 for all vertices j connected to I. Well, I just now follow it. So if d sub I was 0, then all its neighboring vertices must also have entries 0. Then all their neighbors must have entries 0, and I will just now go to everything in the graph. So this means that every every slot must be 0, but I was given a non-zero vector. Okay, so this is the first thing. Now comes the key algebra, which I broke into 3 steps, but I have written everything down. The very first step I have done over here, that because I mean, regardless of how I use the equation, this first part is valid, no? And that means, and I'm going to therefore use this equality. All right. So I need to show that Q is positive semi-definite. So let's examine. We'll take Q of any arbitrary vector X, which remember has slots X1 up to Xn. All right. So I calculate its quadratic form. Okay. So, all right. So this is the quadratic form, and let us see how this is coming. So let's go back and look at the expression for the quadratic form. What was it? I calculated the sum of xi squares, and then for I less than or equal to j, I subtracted this. So all that I have done is that the term I equal to j, I have pulled in the first slot. So the second one will become I less than j, and the first one will have coefficient now 1 minus nii. Okay, so this is what I've gotten over here. 1 minus nii times xi square is this. Okay, so now what do? we follow a clever calculation. Okay, so you see this. Uh, yeah, so just
Excuse me.
one
Shouldn't that
second.
be minus? Shouldn't that be minus before Nij in the second sum?
Yeah, yeah, you're absolutely right. You're absolutely right. That was a mistake. Okay, all right. So now what happened over here? Um, okay. So I was trying to look over here, but we are not there yet. So what did I do? Ignore the highlighting. All I did was a little bit of algebra over here. Okay. So notice that in the first three steps, or in fact in all the steps until that are displayed, the second term, I have not done anything to it. Okay. So the entire action is going to be in the first term. So let's see what has happened. It's very easy. I have simply multiplied by di and divided by di. I can do that because each di is non-zero. Likewise, I have also divided by 2, but multiplied by 2, which I want to put inside. Okay. Uh, yeah, except now. Yeah, just give me a moment. I notice a bug over here, which is now I would like to use this formula and simply plug in for this term. Okay. Uh, yeah, just give me a moment. So there is a mismatch over here because what I would like to do is this the 2 minus for this quantity. I simply want to replace it using the other side, but now there is a mismatch of 2. So what happened over here? Yeah, just give me a moment. What did I miss? Okay. So what I missed was, of course, I made a mistake over here. Yeah. So the mistake that I made over here is in copying the formula. So let's recall and see what I did. Uh, yeah. So here is the mistake. Sorry about this. Yeah. So the mistake is I have to correct this mistake everywhere. Uh, you see, the NII is also going to come with the coefficient 2 when I do the algebra. That's my mistake. So 2 minus 2 NII. So, okay. So this 2 is going to be here and the 2 is going to go all the way, propagate all the way until here. Okay. So let's take up the thread. All right. So So I have simply replaced this. Factor 1 minus NII type by 2 times, and I have divided that by this 2. What this allows me to do is that I recognize this first term over here, and I replace this quantity by the second term. Okay. So I'm simply directly plugged it in. Let us notice what happened over here. Xi square is the same, 2di is the same, and this term Nij times dj is precisely what I have taken from here. I have replaced the single summation actually by a double summation, because notice what is going to happen. When I replace this, I is fixed, but then I have sum over j not equal to I. So for every I, now I'm taking a sum for j not equal to I. That just means it's a double summation with I not equal to j. Okay. So just a matter of algebra. Okay. So everything okay so far? Now what I'm going to do is I'm going to break this into two parts where I is less than j and I is bigger than j. Okay, so when I is less than j, I've directly copied this. There is no change. But when I is bigger than j, I'm going to get the same terms, right? But I'm going to now switch the role of I and j. Therefore, this sum is also over I less than j. And I have literally copied the same thing. Nij is Nij. D sub j now becomes D sub I. D sub I becomes D sub j. And the index I here again becomes j. Okay. So if you're roughly following, it is okay because this is just algebra, nothing else. All right, so now I have summation over I less than j in all three terms. So I just take it out, and I notice that what I have inside is that this Nij is common, and I take di times dj as common thing. Therefore, I get some denominators. So over here, the by 2 has also come. So the denominator will become xi square divided by di square, xj square divided by dj square. And this just becomes a sum of squares. Notice that the middle term also works out because when I expand this square, I'm going to get uh, di times dj in the denominator, which will cancel out with this one, and the 2 times that will cancel out with this one will give me the second term. Okay, so some algebra. The final expression is very nice though, because remember why I wanted to do this. Ignoring all the algebra, finally I have shown that for any vector x whatsoever, I have obtained it as this summation. And this summation is manifestly positive, non-negative. Why? Because this is a square. Nij is the number of edges. And once again, we come up against this, which is that di and dj. Remember, d was assumed to be a vector that was greater than or equal to 0 in each slot. Okay, so I get this form to be positive semi-definite, which proves the second point for me. But now the third point is telling me actually what the radical is, that the radical really cannot be anything more than the rational multiples of d, this d. So what are we saying? That these three things are equivalent. If q of x is equal to 0, if and only if x is a multiple of the special vector, well, look here, this is easy. Because if q of x is 0, then this quantity has to be 0. Well, that means that every summand has to be 0. Okay. So if I and j are not connected, then it's okay. Then this itself gives me 0. But the moment I and j are connected, this is strictly positive. This is also strictly positive because remember d is a sincere vector. And that means this quantity has to be 0. That just means that in slots I and j, the vectors x and the vector d have to be proportional. Okay, anytime I and j are connected. But once again, I use that the graph is connected. And so that means that the vectors x and the vectors x and d have to be proportional. So if the form is, if the quadratic form of x is 0, then I see that x is proportional to d. But of course, anything that is proportional to d is going to be in the radical. And if anything is in the radical, then I complete the circle and say that radical means the form of x with anything is 0. So in particular, the form of x with itself is 0. And that's exactly, up to scalar 2, that's exactly the quadratic form. So I have shown that qx is 0 if and only if x is a rational multiple of d, if and only if x is in the radical. Okay. So just to see, I have proved the key lemma. Okay. The reason why I'm getting only so just one second. The reason why I'm getting only rational multiples is, remember, I'm working only in Zn. Okay. So when two vectors are proportional, that means that the common ratio is going to be an integer by an integer, which is going to be a rational number. Okay. So any comments or questions?
Yeah. So do we a priori know whether D has integral entries or
Yes,
D can have
because
real entries?
that's the hypothesis. So you see, I mean, this seems kind of, you just get so much out of this very simple thing. No, but you have to be given this very special vector. Without that, nothing is coming, right? So in order to apply this lemma, I have to have a vector with all of these properties. Must be a radical
No,
vector
I'm
which
asking,
is
do we know that the components of D are rational a priori?
okay.
That's what.
So let us see where this is happening. Everything is happening. So everything is happening in Zn. So even though I keep on saying vectors, every single thing that you see is an integer vector.
Okay, thanks. Yeah.
Yeah. So
There is a question in the chat.
yes.
How are we defining the radical from Tanisha Talikar?
Yes. So let me go back. Radical of a form is again, if you think in terms of perpendicularity, it just means all those vectors that are perpendicular to everything else. So the bilinear form vanishes on every single vector. When you take that vector and calculate its bilinear form with any vector whatsoever, I always get 0. Okay. Anything else? Very well. So, uh, so I use this. And what do I do? I'm going to take the help of this. I'm going to take the help of this lemma to get to Dynkin diagrams via the associated Euclidean diagrams. Okay. So here is the theorem. Exactly one of the three things happen for a given connected graph. Remember, the graph is absolutely arbitrary. There could be multiple edges, loops, whatever. Okay. So if the graph is Dynkin, then Q is positive definite. If the graph is Euclidean, then Q is positive semi-definite. So the way it is stated, okay. So if the graph is Euclidean, then Q is positive semi-definite. Uh, and notice that in view of one, okay, so not quite. Let me just state it the way it is, written. It's very clear. So the given graph is either Dynkin or Euclidean or neither. Right? That's the trichotomy. So in each case, we have a detecting criterion. In the first case, Q is positive definite. In the second case, Q is positive semi-definite, but it is not positive definite because there is a radical. But in fact, this is saying something more. It says that the radical is all multiples of this special vector D that I wrote down yesterday in the diagram. Again, notice that I'm not taking rational multiples. I'm taking only integer multiples. And we will see why this is the case. It's a simple matter. Otherwise, if any Q that is not Dynkin or Euclidean, we are saying that, well, I will be able to find a not only non-zero, I will be able to find a positive, I will be able to find a positive vector, that is every slot greater than or equal to 0. Uh, I should have said non-zero vector, right? X not equal to 0. I'll add that. X with okay. So this is yeah, it is implied because what we are saying is, notice, not only is the quadratic form 0, the bilinear form X evaluated on every single basis vector is less than 0. So if you want to think in terms of angles, strictly speaking, I cannot if you are using Euclidean space as your intuition. But if I can think in terms of angles, what is this saying? That the angle between X and alpha is what kind? It's an obtuse angle, right? Because if I think of the inner product as usual cosine, then this says that cosine is negative. So the angle is obtuse.
I have a question here. So isn't the converse true as well in each statement?
Yeah, so right, exactly. But you see that follows, no? In the sense that, okay, so okay, let's just see. So if Q is positive, okay, so if Q is okay, let's see. So if Q of anything is less than 0, then I cannot be in the first case. I cannot be in the second case. So I have to be in the third case. Right. Similarly, yes, thanks for pointing that out, because the theorem is stated, the statement is such that It really is a characterization. Similarly, if Q is positive definite, right? Can you be Euclidean? No, because there is a radical. Can you be here? No, because there is something which has Q negative. So if Q is positive semi-definite, then I have to be Dynkin. Similarly, if you are positive semi-definite, then you cannot be in the third case. And so here there is a slight thing. If Q is if the quadratic form is positive semi-definite, then I could be Dynkin or Euclidean, right? But if I am positive semi-definite and not positive definite, then there has to be a radical. So then I have to be Euclidean. Because if I was Dynkin, then I would be positive semi-definite. Right? So yes, this is definitely worth realizing that just calculating what the quadratic form is like, I will be able to tell what kind of quiver it is. If the form is positive definite, then I am Dynkin. If the form is positive semi-definite, then I am Dynkin or Euclidean. And if there is a radical, then I am Euclidean. Otherwise, otherwise it's something else. Okay, so how do I do this? And of course, I'm going to catch this by means of this special lemma.
There is a question. So what are alpha I here?
Yeah, so let's remember that always good to remember terminology. So in my everything is happening in Zn, that is the space in which I am operating. And remember that alpha I is the standard basis. It will always be the standard basis for us throughout the lecture. So alpha 1 is 1 0 0 0 0, alpha 2 is 0 1 0 0 0 0, etc. Okay. Okay. So this proof we will just sketch, and we will do the final details in the last details in the tutorial. So what do I do? Of course, I start with 2. So yesterday we drew these Euclidean diagrams, and I wrote some special integers on each one of the vertices. So I simply take that to be the D, and I check that the hypothesis of the lemma are satisfied. Let's once again look at what the hypotheses are. They're very easy to check. Each vector, in fact, the given vector itself is, the given vector already is positive in each slot. So all you have to do is that it is a radical vector. But this is an explicit check, because once you have the picture, you can simply write down the bilinear form. And all you have to do is that the given vector, just looking at the form of the matrix of this form, I just have to see that it is perpendicular to everything. So yesterday in the tutorial, we carried out this check for for D4, D4 tilde and AN tilde. So it's a simple check. All right. So that takes care of most of number 2. Okay. But we are also saying that the radical of the form is exactly integer multiples of D. The lemma does not give me Z, the lemma gives me Q. But if you notice what the vector D is, and you know what, let me just go back to the picture. We'll go through some rough work here, but these are the pictures yesterday. Okay. So the vectors are written over here. The labels and at each dot tell me what the corresponding coefficient is. Okay. So this one is really, the vector is 1 1 1 1 everywhere. This vector is 1 times alpha 1 plus 2 times alpha 2 plus 2 times alpha 3, and so on and so forth. Okay. So notice that all of these vectors are greater than or equal to 0. And notice that so the only vectors that I'm admitting are the ones with integer coordinates, right? What I already know based on the lemma is everything in the radical is a rational multiple of the special vector. But can a non-integer multiple of this be in Zn? And the answer is no, because you just look at this 1. If I'm multiplying by a non-integer rational number, I will get that non-integer rational number in the slot. No? So I cannot have a vector in Zn by multiplying this by anything other than an integer. Does the same thing work over here? Well, as far as these vertices are concerned, maybe I could multiply by something that is denominator 2, but there are these ones sitting. And likewise, you see that in every single picture, there is at least a single one. So here I have ones. Here I have two ones. And here there is this very nice one at the end. Okay. So that takes care of proving number 2 completely. Let's take a look at the statement. So, right. So number 2 said that if I'm Euclidean, then just by inspection, I apply the lemma to the chosen vector D and deduce that the form is positive semi-definite. And just because D is 1 in some slot, the radical has to be only this. Okay. All right. So now I come to number 1. So now I'm going to do Dynkin case. One way to do the Dynkin case is to actually just go case by case and see the form, write down the corresponding matrix for the bilinear form and use Sylvester's criterion to show that the form is positive definite. We carried this out in the tutorial for some examples, but we'll do a trick over here. For this, I just want to sort of say something very, very easy. Let us suppose I have some graph, okay, whatever, some multiple edges, something, whatever, anything. So I have the quadratic form. And now I take some vector over here, x1, x2, x3, x4, x5, whatever, something, right? And I want to calculate its quadratic form. Okay. Let us suppose that this x1 is actually 0. Then just think about it. When I calculate the quadratic form for this vector, it is as if I can simply ignore this vertex altogether, because it does not contribute, no? This vertex over here, it's not going to contribute. The corresponding xi, which is going to come in the formula, is going to be 0 everywhere. So it's as if you simply, it's as if you take this and you simply delete that, and you take the rest of the quiver and take the vector as it is and calculate its quadratic form. Just think about it for a moment if you need to. Right? If you want, we can go back and look at the formula. If some xi is 0, then that xi will just give me 0 here and it will give me 0 here, wherever it occurs. I just ignore it. How does this help me? This helped me in a very simple fashion. Remember that every Dynkin diagram, so I'm starting with a Dynkin diagram, right? But every Dynkin diagram has a corresponding Euclidean diagram where I just add a vertex. So for type A, I just put another vertex and complete the cycle. For type D, I add a vertex at one of the ends so that there are two trivalent vertices. And likewise for E, I add one vertex, correct, somewhere. The point though is that I then go to this extended diagram and calculating the quadratic form of whichever vector I have in mind earlier is the same as calculating the quadratic form of the same vector regarded as a vector in Zn plus 1 with the extra slot 0. Yeah. So q of x in A is the same thing as q of the same x regarded in A tilde. Okay, that already gives me that this form has to be, that q of x has to be greater than or equal to 0 because I showed that A tilde is positive semi-definite. But can it be 0? Well, look, we showed that the only way the quadratic form is 0 is if I have a scalar multiple, if I have a multiple of this very special vector. And the special vector is non-zero in each slot. So the moment I have a non-sincere vector, if you will, the quadratic form is going to be always strictly positive. End of the story. Okay. So the third one is a little bit of a job, but it is easy. Okay. So you might think, oh my God, I have some arbitrary graph. How am I going to deal with this? And the answer is as follows. You will always be able to locate a Euclidean sub-diagram and then use that sub-diagram to get a bad vector. Okay, so let me just sketch this and the details we'll do in the tutorial. Okay, so there are two parts to this. One, to locate a Euclidean subgraph, and then what to do with that subgraph. Okay, so first let's first locate a Euclidean subgraph. All right, so if the graph has a cycle, then what? Let me go one by one. Okay, so if the graph has a cycle, what do? I just take that cycle, ignore everything else. I should say what I mean by a subgraph over here. By subgraph, I mean take some of the vertices and some of the edges. Of course, if I want to take an edge, I have to take both vertices that it connects. But I'm allowed to delete some vertices and among the remain and all edges, connected to them. But I'm also allowed to delete some of the edges keeping the vertices. That's what I mean by a subgraph. So having having said that, what do I do? If the graph has a cycle, just keep the cycle and erase everything else. That's your a n tilde. Okay. Otherwise, otherwise I will have a tree. You know what? Maybe what we should do is we should have those Euclidean diagrams in front of us so that we will see what's going on. Yeah. Okay. So these are the diagrams. So remember, I have an arbitrary graph. My task is to locate a Euclidean diagram. If there is a cycle, then if there is a cycle, I get this. If there isn't a cycle, then I have a tree. So I start looking at degrees of vertices. Is there a vertex of degree 4 or bigger? If there is a vertex of degree 4 or bigger, then I simply take that vertex. And by the way, so now the number of there cannot be multiple edges also between vertices, because the moment I have multiple edges, if I have multiple edges, okay, let me just write this here temporarily.
I have a question, please. Can you recall what is mean the degree of the vertex?
Degree of a vertex is simply the number of edges that are incident on it.
Okay, thank you.
Yeah, so just number of connections. All right. So I should also say that there are no multiple edges, because if I have a multiple edge, then this itself gives me a cycle, you see. So yeah, I should say one thing. What is a? So this a n tilde you have to kind of understand. What is a1 tilde? A1 tilde, that means that I have okay, or maybe A0 tilde. So I'm adding a all right. So I'm getting a bit confused with the terminology over here.
I don't think we define A0 tilde. We just
okay.
define
so
A1.
Right. So A1, right. So but A1 tilde is going to be just one vertex and a loop over here. And A2 tilde, so okay. So A2 tilde means what? I have correct, absolutely right. Thank you. So remember, in order to get AN tilde, what so now my confusion is cleared, that brain fade. Okay, an tilde means I start with n vertices and then add a loop, correct? So a1 tilde, so if I have a1, then a1 is just a single dot. Then a1 tilde has to be defined, and the way I define it is just by adding a loop to that. Whereas an
No, I think
sorry,
A1 tilde would be two vertices. Yeah, you always
correct.
add one vertex to AN.
Yeah, right. So if that is the case, then I do want to make a definition that a0 tilde is a loop, because I want to include that as a case. So I'm adding a vertex and completing the cycle. Okay. In any case, over here I do not need this. So if you do not like it, delete this. But if I have a1, but if I have a1, then I just have a single vertex, and a1 tilde means I add a vertex. If you like, I will add it above and complete the cycle. That means I just get two parallel edges. So this is a1 tilde. Right? Okay.
And by the way, your video has stopped.
Oh, okay. Just give me a moment, please. I don't know how that happened, but okay. Is it okay now?
Yes, yes.
Okay.
There should be a
Uh,
timeout.
Might be. Okay. All right. Yeah. So just to recap, I have any graph whatsoever. If there is a cycle, including maybe parallel edges, I simply get a Euclidean diagram of type A tilde. Otherwise, I have a tree. So I look at the degrees of vertices. If something has degree 4 or bigger, I keep that vertex and I keep 4 of its neighbors and I drop everything else. What have I obtained? I have obtained D4 tilde. Right? So remember D4 tilde, D3 tilde. I keep making a mistake because the number of vertices in the Euclidean type is one more than n. So that is D3 tilde. Okay. Okay. So that means that I have taken care of uh, if there is anything of degree bigger than or equal to 4. Okay. So that means that now the degree of everything is less than or equal to 3. Okay. So if there are two vertices of degree 3, then I simply take those two vertices and I take the unique path between them. Remember, this is a tree, so any two vertices have a unique path. I simply take that path and then take the two vertices of degree 3 and I have a dn tilde. Okay, so I have taken care of the case where there are at least two vertices of degree 3. Okay, so that means that there is a single vertex of degree 3. And now I'm going to be able to locate one of these in there. Because what I do is my graph is going to be of the type, let me just go over here. And this is a mistake that I should correct, not D4 tilde, but D3 tilde. So this means I have at most one vertex of degree 3. If I have one vertex of degree 3, then I have this kind of central vertex and 3 spokes kind of diagram. Then I see, well, how many edges there are on each side. If all sides have at least at least two edges coming out of it, then that's an E6. Otherwise, at least one of them has exactly one edge going out. And then I go and take E7 tilde and E8 tilde. It's a matter of some details. Okay. So I hope that the kind of argument is clear, even if all the details are not clear. There is zero algebra going on over here. There is just some very basic graph theory. Okay. Any questions on this?
There are two unanswered questions in the chat. So,
Okay.
Vector x or alpha I has any relation with the vertices of the quiver?
Okay, so I'm not sure what is going on over here. So remember, alpha I is the special basis vertex. Alpha I is always 1, 0, 1 in one slot and 0 anywhere else. Okay, I imagine that the question is about locating this special vertex, special vector x, which I have not come to at all. All right. Maybe I will say
I have another, yeah.
Yes.
Sorry.
Yes.
So A0 tilde won't make sense because A1 tilde at least has some orientation which will keep it finite dimensional algebra.
Okay.
A0 tilde cannot be made finite dimensional, yeah, unless you put relations. So I don't think it will make sense.
Okay, so I don't really know about this because it's a matter of terminology. The other, it's not even defined. I mean, in order to define an tilde using our definition, you first have to have an, right? And even in the case of a1, I had to make a definition. No, okay. So I connect it with both ends, which are the same. So I do get the Kronecker double arrow quiver.
Yes,
Just give me a
Kronecker
moment.
quiver, yeah.
Yeah. So just give me one moment, please, since we are discussing this. I mean, it's a degenerate case, but I want to see that whether there is a. Yeah. Okay. So the reference does say that A0 tilde has one vertex and one loop. This is his
Okay.
definition. I mean, it's a matter of definition, no, because you do not have an A0 to begin with to connect with the extra vertex that you are adding. So what do you do with the extra vertex? So it's a definition, and this is how he's choosing to define it.
Okay.
Anyway, going back. So for an arbitrary graph, I located a Euclidean subgraph. And if this Euclidean subgraph is not the whole thing, Euclidean, by the way, I will get a Euclidean one or even a Dynkin. The entire graph would be Dynkin or Euclidean. If not, then what is going to happen is that there will be a Euclidean subgraph and some extra thing. Okay. So what is this extra thing? The extra thing could take two forms. That there are some extra vertices themselves. If that is the case, I simply take the located Euclidean subgraph, and I just take the same vector D. But remember, the extra vertices that I have, I'm just going to put zeros on that. Just the fact that there are connections from this Euclidean subgraph to those extra things means that there will be extra ni's coming in, you see, in the formula. And so I will get a negative answer. This is something to check. I don't want to get into the details. Another case is that the Euclidean subgraph that I have, my graph has no other vertices, just some extra. I switched the two. Okay. Okay. So sorry about that. So the first case is that the Euclidean subgraph that I got, there are no other, that contains all the vertices. The only thing that I have done is deleted some edges. If that is the case, then I simply take the same D that I took earlier. But now the Q of this D is going to start becoming negative, you see, because if you look at the formula for N, if you look at the formula for Q, what has happened is that this term will stay the same. But now these Nij's have become bigger. At least there is something bigger, no? So if I take the original vector D, which gives me Q of D equal to 0, then I have just made something else more negative. So I will get something strictly negative. That's what happens if that's what happens if you have no extra vertices. If you have extra vertices, then you do something very simple. You just take one of the extra vertices that is connected to your Euclidean subdiagram, and simply and just put a 1 in that slot. And just to have the calculation work out, what you should do is you should not take D, but you should take 2 times D. So this is what I have written over here. So if you have some I outside the subgraph but connected to the one that I located, then you just take 2D plus alpha I, and it's a matter of small calculation to see that the given condition is satisfied. Okay. So I don't want to get into the details of this because we really need to get back to representation theory. Okay. So any questions now? Now, if there are any unanswered questions, I can perhaps we can try to discuss them. Is there anything?
Yeah, one more. So is it always the case that some end vertex xi is 0 since we need a non-sincere vector? I think this was about the proof from Tanisha Talekar.
Okay, so I'm sorry. So this is the okay. So looking at the statement once again, please. Let me see if I can just see the chat.
Yeah.
Chat. Okay. Sorry, somehow I'm not seeing the most recent.
Can I just explain it?
Yes, please go ahead. Yes, please go ahead.
So for the proof, we took the case where if x1, which was the end vertex, if that was 0, then we can take di to be 0 at that and then embed it into some Euclidean graph.
Yes. So you're talking about the proof of 1 here, right? Yes.
So in case if one of the vertices in the middle are 0, will that cause any issues? Like, will it make the graph disconnected?
Right. Okay. Fine. Fair point. Okay. All right, let's go and look at that. Yeah, so I need to show that Q is positive definite, right? So let me just gather my thoughts over here. Yeah, what do we, so okay, I have, right, so okay, now I understand. So I have an arbitrary X, and yeah, but you see, all right, no, here is the thing. I am not taking a Euclidean I'm not taking a Euclidean one and disconnecting it. I'm starting with a Dynkin diagram. I'm starting with a Dynkin diagram and just putting an extra vertex. So there is no issue of disconnection over here, right?
So Qi being 0 at any particular vertex won't give rise to some issue.
No, because the vector is sincere, no. Sorry, the vector is, see, the vector that I have taken is non-sincere. So even if it is 0 somewhere else inside, it still doesn't matter.
So all we need is it for it to be 0 at some vertex.
But it doesn't matter. No, whatever vector you have given me, x, by putting 0 in the added spot, I have gotten a vector in the extended Euclidean, in the extended, in the Euclidean one, right? And so Q of any such vector is going to be positive, strictly positive, because the only ones for which Q is 0 are scalar, are multiples of D. So okay, maybe one point to say, to clear the confusion. In order, see, Q of every non-zero vector is 0. So if your vector is 0 in some slots, it has some 0 entries, but non-zero entries in somewhere, then it is okay. Just like take the standard inner product. No, if I take the standard inner product, then EI dot EI is 1, even though the vector is 0 in many slots. Every single non-zero vector has Q of it to be strictly positive. I don't know if this helps. Okay, is that okay?
I think that answers my.
Yeah. Okay, very good. So so these details let's do later. And I said we want to get to representation theory, but unfortunately we have some more work to do. Okay. So let's take stock. We have proved for the original goal that we had. What have we done? We have proved, not only have we proved the equivalence of 2 and 3, we have proved something more. We even have these other nice diagrams, the Euclidean diagrams, for which I know that they are precisely the ones where the form is positive semi-definite and not positive definite. And I also know what their radical is. I'm going to use these once again, but not today. All right. So let's gather some more information about this situation where Dynkin or Euclidean. I will include the Euclidean case for now because it doesn't really require much extra work. Soon we will specialize to the Dynkin case. Okay, so I'm going to call roots to be a very special set of vectors, integer vectors in Zn. And I'll sort of give the game away. The roots are going to be important for us because the dimensions of indecomposable representations are going to be roots. When we analyze the when we analyze the cases of interest, this is what is going to happen. That's the reason why I want roots. Okay, so what is a root? My diagram is Dynkin or Euclidean. So I simply take those integer vectors such that the form is either 0 or 1. So it's less than or equal to 1. Remember, the form has to be an integer, right? The formula is an integer formula. If the value of the form is 1, I call it a real root. Otherwise, I call it an imaginary root. This imaginary case will go away soon because the imaginary case is going to occur only in the Euclidean situation, whereas our focus soon is going to be on the Dynkin case. Okay, so there are some facts about this. Each standard basis vector alpha is a root. Why? I have to calculate Q of alpha I, no? So what is Q of alpha I? Let's go back to the formula. You just look
It
over
would
here.
just be one, right?
Okay. Now just, yeah, correct. Exactly. It would be one because you're looking at this. You're looking at this. However, what if there is a loop to itself? And we did say that this A0 tilde rears its head once again. If there is a self loop, then I will get 0. But only in that case. Yes. So let's write this down. So Q alpha I is equal to 1. 0 if I have this picture. Nonetheless, it's a okay. So if alpha is a root and delta is in the radical, that means it's an integer multiple of the special vector. First of all, if alpha is a root, minus alpha is a root. What happens? What is Q of minus alpha? What is Q of any scalar multiple of alpha? It's a quadratic form. So the scalar just comes out as a square. So of course, this is perfectly okay. There is no issue about this, right? Sorry, this is a mistake. There is no beta. There is a delta. So what is Q of alpha plus delta? That is Q alpha plus Q delta. This is the general formula, right? Which we are going to use once again, and then plus the form of alpha and delta. And now everything writes itself out, no? Q alpha is a root. Therefore, this quantity is either 0 or 1. This quantity is 0. Remember, delta is perpendicular to everything, including itself. And of course, alpha delta is also 0. So both of these terms are 0. So Q of alpha plus delta is. So what this says is that in the Euclidean case, you can add any multiple of delta. You'll still get a root because I can keep adding delta, no, or subtracting. Okay. Now we come to the Dynkin case. Then there are no imaginary roots, and in the Euclidean case, of course, they are just the multiples of D. This is straight from the lemma, no? Because Q of something is 0 means it's a multiple of D. We saw that. This number 4, there should be some kind of drum roll over here, right? I'm going to put an exclamation mark. Perhaps a red exclamation mark. What this says is that every root, remember, root is just means a vector of length 1 or 0. You can just keep the length, sorry, Q is equal to 1 in your mind. What does it say? It says that if I write a root as in terms of the standard basis, alpha, so so in terms of so in Zn the vector is just k1 k2 up to kn. That's what I have written over here. Okay, then all the ki's are positive or all the ki's are non-negative or all are non-positive. You cannot have mixed signs. This is something amazing. Okay, just the fact that it is a root means that all the non-zero coefficients are positive or all the non-zero coefficients are negative. Let's see why this comes. I mean, it's a striking result, but the proof is not difficult. So let us see. What do? I write alpha as a, I just club the positive case together and the negative case together. So in this part, I have all the positive things, and in this part, I have all the, let's say, rest of them, including 0 also, doesn't matter. Or you can just drop those terms. And you can say here I have the positive coefficients, and here I have the negative coefficients. So remember what this means is that the two sets of vertices involved in the first sum and in the first part and the second part, they are disjoint. Okay. All right. So what happens now? Let's just calculate Q of alpha. It's the same formula as before. The the additive formula. So this says that Q of alpha plus Q of alpha minus, and then this form evaluated on alpha plus and alpha minus. Now I claim that this quantity over here is non-negative. Just think about what is going on. Look at the formula. Look at the formula for the bilinear form. Remember, alpha plus and alpha minus, they do not share any vertex where both are non-zero. So let's go and look at the formula for the bilinear form. I'm just going to get sums of such terms, right? There will be no, this case will simply not arise when I open the parentheses. So every term that I get is going to be negative when I just calculate alpha I occurring in one and alpha j occurring in the other. All of these things are negative. However, the coefficients that occur in the coefficients that occur in alpha plus are all positive, and the coefficients that occur in alpha minus are all negative. And the individual NIJs that I get are all, they're all coming with a negative sign. So every single term when I open the parentheses turns out to be a positive term, or zero if Nij is zero. But it's a connected thing, remember? So something is connected with something. If I have two sets of vertices, they just cannot. Okay, no, 1 second. No, not necessary, because you could just have two completely distant set of vertices and sum of the coefficients zero. Never mind. Nonetheless, this is going to be a non-negative entity. Therefore, Q alpha is greater than or equal to Q of alpha plus Q of alpha minus. Okay. So what do? What I want to say is that every root is positive or negative. Okay. Well, what do I know about Q alpha? I'm in the I am in the case where it's a root, and I'm in the in any case it's a root. Therefore, this is equal to 0 or 1. Okay, so let's examine the cases. If Q of alpha is equal to 0, then that means that this sum is 0. What can I say? I'm in the Dynkin or Euclidean case. That means that every Q value is non-negative. So this has to be 0. This also has to be 0. So they both have to be scalar multiples of my special vector D. But alpha plus and alpha minus, they both were sitting on different vertices. They don't have anything in common. So this just cannot happen. Right? Unless both alpha plus and alpha minus are 0. But remember, this is a root. A root is by definition a non-zero vector. All right. Let's look at the next case. If Q of alpha is equal to 1, then that means that they are both 0, or one of them is 1 and one of them is 0. But if one of them is 0, then it must be a multiple of, once again the same thing. It must be a multiple of the special vector D. The special vector D is sincere. So if the one for which I'm getting Q to be 0 was a non-zero vector, let's say alpha minus, then this alpha minus would have its support on every single vertex. So that would mean that the entire vector is alpha minus or alpha plus, but that's exactly what we wanted to show, that the root is positive or negative. So I'm going to delete this question mark, and this is an interesting point. If there are any questions, if something is unclear, please ask me now. The proof is maybe not so important, but using this fact is extremely important, that every root is positive or negative. I should have said earlier that whatever we are doing now, in Lie algebras, have you reached the root systems yet? In the morning lectures?
Yeah, it was started today.
Okay. So whatever we are doing today is everything is applicable. So you are going to see that every root is so if I have a root, then minus of a root is a root. Every root is either positive or negative. All of these things are going to come even over there. So this is very important. All right. So that's fact number 4. There is number 5, which I will not do because that is specific to the Euclidean case, which we will come to if we need it later on. Let us show that if Q is a Dynkin
There is a question like before you go to 6. That's how are we defining alpha plus and alpha minus?
Yeah. Right. Let me just do something very simple. Let us say that let us just say that alpha is equal to 2 alpha 1 plus 3 alpha 2 minus 4 alpha 3 plus whatever plus alpha 4 minus 6 alpha 5, 6 alpha 5, something like that. All I'm saying is that this alpha plus consists of the first term, the second term, and this term. And alpha minus consists of this one and this one. I'm just separating out the positive and negative coefficients. And where this was useful is that you know what, let me not mix this up. Just the numbering is unimportant. So it is this one and so this is alpha plus and this is alpha minus. The way this separation really came into the issue was in justifying that this quantity over here is non-negative, because when I distribute the parentheses, you see, when I calculate alpha plus bilinear form with alpha minus, the coefficients that I'm going to get, for example, I will get minus 12 times the form of alpha 1 with alpha 5. The form of alpha 1 with alpha 5 is minus n15. You see? So I'm going to get minus 12 times minus n15. That's a non-negative thing. If n15 is 0, if there are no edges, then I will get 0. But otherwise, I'm going to get a positive number. So likewise, when I open the parenthesis, everything will turn out to be positive. That was the key thing in the proof over here. Okay. So any other question? I hope, is that okay now?
Then this alpha is not root, as every root is positive and negative.
Okay, but remember that we were in the world of that's exactly right. But that is the contradiction that we derived. But instead of doing a contradiction, what we said is that if I have a root, then if I have a root, let's just revisit the one case. Then that means that one of these has to be 1 and the other has to be 0. But the one that is 0 will have to be a scalar multiple of a sincere vector. But a sincere vector sits everywhere and it cannot. Therefore, that part itself has to be 0. So what we said is that under this assumption, what will happen is that alpha will turn out to be either alpha plus or alpha minus. The other one will just be 0. That's how we got it. It's a proof by contradiction, if you will. Is that okay? Or all right. So let me make partial amends because I just didn't write anything. I will just say deduce that alpha plus or alpha minus is equal to 0. Okay. So now let's focus on the Dynkin case. Right. So what this means is that each of Q alpha is 1. There are no zeros anywhere. Okay. Now I claim that the number of roots is finite. But this is okay because if you want a formal proof, you see what you're doing is that think of this Zn as sitting in Rn. Okay. And I have a positive definite bilinear form. that makes this into a Euclidean space. This Euclidean use is not the same as the other Euclidean, okay, Euclidean diagrams. Maybe call them affine diagrams. So I have a Euclidean space. I can really think of actual angles, right? I can take an orthonormal basis, etc. This Zn is sitting as a lattice inside that. So it's a discrete set. But this Q alpha is equal to 1 means that all of these vectors are sitting in a finite part. No? So this is a discrete set in a compact set. Therefore, it has to be finite, if you will. You know, I should really not say unit sphere. I was avoiding this issue, but let's do this in a sphere. If Q alpha is equal to 1, what is actually the length of the vector? So how do I define the length of a vector in an inner product space? It's the square root of v dot v, right? So if Q alpha is equal to 1, what is the bilinear form of alpha with itself? Is it 1? Okay, this really is checking back. So remember that Q of alpha is not equal to alpha. It is half of alpha. That's just how the formula works. Algebra. So if Q of alpha is equal to 1, then that means that the squared length of alpha is actually 2. So alpha is of length square root of 2. Whatever. It's sitting inside, it's sitting on some sphere of radius square root of 2. And the set is discrete. So it is a finite set. If we go via if we again take the help of the Euclidean diagrams, then we can give a slightly different proof. But I did not do item 5, so this is the way I will get at it. So the number of positive roots. Remember, every root is positive or negative, and minus of every root is a root. So now the roots are just fallen into two halves: the positive ones and the negative ones, which are equinumerous. And this is the number of roots, which I have just written down. We will see some of this and play with the actual combinatorics in the tutorial. All right. So what do I have? Now I focus on the Dynkin type. What do I have to do over here? Going back to the representation theory, what we have to show is two different things. In items 1, 2, and 3, I have shown the equivalence of 2 and 3. So I have to show equivalence with 1. So one direction is that if I have a quiver of Dynkin type, then it has finitely many indecomposable representations. And then the converse, which is if I have finite type, then the quiver must be of type ADE. The second part we will come to later. Our focus is now on the first part. And I will do this by proving something much more. So this is the claim, which is that if I take indecomposable representations of Q and I simply take the dimension vector of that. So for every indecomposable, I simply take the dimension vector. I claim that I will get a positive root of the corresponding root system. So I have to show that this map is well defined. And in fact, I claim that this is a bijection. So that means that I have to show that the map is 1-to-1. In other words, if I know the dimension vector of an indecomposable representation, I can recover the representation. And second, the map is onto, that every single root is realized as the dimension vector of an indecomposable representation. It really is a very crisp theorem. Okay. So this is where we are headed. Unfortunately, we cannot get there just yet because we still need some more work in the root system. So let's do that. And we add another star player over here, which is the while group. So remember, I have Q of Dynkin type, so that means ADE. and I'm going to work in this Zn, there are still no representations. What I'm going to do is I define this sigma I from Zn to Zn to be the reflection that I told you about yesterday. So I have written the formula. Every vector x is going to x minus this quantity. Okay, so this is the formula that I wrote yesterday. So if x is perpendicular, now I can really start using perpendicularity language, right? And angles, because this is an inner product. Okay, so if x is perpendicular to alpha, then this term just dies. So x goes to itself. And where does alpha I go? Alpha I goes to alpha I minus this quantity. This quantity just becomes 2 because alpha I will cancel out with itself. So alpha I minus 2 alpha I. So this sends alpha I to minus of alpha I, and everything perpendicular to alpha I stays fixed. Notice one thing: the length of the squared length of alpha I is 2. So this really is just this formula. However, I wrote this formula because in the Lie algebra course, you are going to see this formula. Over there, it will not be the case that all roots will have the same length. Sometimes roots may come in 2 different lengths. So this is a formula that you should remember. It just boils down to this one. Okay. Key fact: this sigma I, it's a reflection, and so it is going to preserve the bilinear form, which is to say, sigma I of x, sigma I of y. If I calculate their bilinear form, this is going to be the same as x and y. You can of course do the calculation, but come on, just see visually. This is something that is going to take an orthonormal basis to an orthonormal basis. Of course, it's going to preserve the form, right? A plane that is perpendicular to alpha is staying to itself, and alpha is going to minus of itself. So of course, this clearly preserves lengths, angles. So this is a so this preserves the form. If you don't like what I just said, do the calculation. What was a root? A root was a vector of length 1, a vector in Zn of length 1. So sigma of a root is going to be a root because it preserves the form. Yeah, very good. Sigma, so this we already checked. So what does sigma I do to roots? We just said that it sends roots to roots. It sends alpha I to minus alpha I. And every root is positive or negative. So this is a positive root that it's being sent to the negative root. Remember what positive root means? It means that wherever I have a non-zero entry, it is a positive entry, which is the case for the standard basis vector, and this one is a negative one. Key fact: if I take any other positive root whatsoever, then sigma I will send it to a positive. So all the positive roots other than alpha I are going to get permuted among themselves by sigma I. Sigma I, by the way, sigma I is bijective. You know, we just see it's something that is invertible on this Zn. No, its identity on something, and it's sending a basis to a basis. So it's a bijective map. So it's just going to permute the other positive roots. Okay. So how does this come about? Again, this fact is also going to be very important in the for root systems that you will encounter in the Lie algebra. So what do? You just see the formula. Look, now let's take x to be a root. Where is x going? It is going to something. Well, what happens? X has n slots. This formula sigma I changes how many slots? It changes only one slot, right? So if x has any slot other, so if x is a positive root, and if it is other than alpha I, then it will have at least one other slot that is non-zero. So that means some other slot has to be positive. That slot is not changed by this formula. So that slot will still continue to have a positive entry. But we just said that every root is either fully positive or fully negative. So just the fact, just looking at this formula, and some slot is staying unchanged by sigma forces the root to stay positive. See, all of these are kind of small miracles, okay? So again, a key fact over here. The group that is generated by these sigma i's is called the while group associated to Q, and this is a finite group. So why is this a finite group? All right.
Excuse me, sir, I had a question.
Yes.
We are defining the roots to be elements in Zn such that their lengths are 1, right?
Yeah. No, sorry, not lengths. Because if I think of their Q is 1, their Q is 1. So the length is squared length is 2. That's just because how the length is defined. You see, the length is square root of V dot V, no? So the roots are such that Q of alpha is Q of X is 1. But go ahead. Yes, you were saying.
Sir, I'm just having some trouble thinking of any roots which are not alpha i's. Like, can you give me an example of a positive root which is not alpha I?
Okay, so we will see this in the tutorial. But in fact, what you can do is that just work. I mean, the recipe is already there. No? Take one root for an and just apply the sigma I to it. You are going to get other roots.
Okay, right. Yeah,
Right?
I understood.
Huh. By the way, what you said, I'm not at all dismissing the question. This is very important. You have to do these calculations. See, this is kind of a very dual nature of the subject. So we are saying roots, and then we are doing all this kind of theory, while group, simple reflections, and so on and so forth. But in the end, we are really just talking about a list. So if you wanted, what you could do is that just do case by case analysis. But building these terms really makes the whole thing conceptual. But the flip side is that if you think, okay, theory, yes, I can do all the theorems. You really, you cannot do anything with this unless you actually get your hands dirty with examples and calculate what all these things mean. So calculating the root system of type AN is the very first thing, and it has to be done. Okay, it's not enough in general, but this much you have to do. Okay. I think Sayre calls this digging roots and lifting weights. So the roots you saw, the weights we will not see, but in your early algebras course, when you come to representation theory, you will see what weights are. Okay, anything else? Oh, we have just 1 minute. Let's see what we can do. All right, so the while group is the one that is generated by these. This is a finite group. Why is this a finite group? Well, because you see, these are all, a while group is going to permute the roots. No, the number of roots is finite, and in particular among the roots, you have a basis, right? All the alpha is their roots, and that's a basis. So all of these are linear maps, so they will be completely determined by what they do on the basis. Well, how many possible things can it do to a basis? The number of roots is finite. So the number of permutations that W can induce on this finite set is also finite. So in particular, the total number of possibilities for any element of W applied to alpha 1 up to alpha n, whatever those n images can be, is only a finite number. And the moment I tell you what the images of alpha 1 up to alpha n are, the entire element is decided. It's a linear map. So W is a finite group. All right, so let me, because it's already 3:30, I can't really cram anything. It's just not the right thing to do. Let me just say where we are headed. What we are going to show is that if I take a positive root, then I can start applying reflections to it in such a way. In fact, let me go back and just show the following. This claim. Okay, key fact. Ignore this Coxeter element. Some special element. Okay. So what it says is that if I take a positive vector, and then then there is some way in which I can apply sigmas to it so that at least one coefficient becomes negative. This fact is going to unlock the entire proof of whatever we said, as we will see tomorrow, based on the fact that the effect of applying a reflection functor to an indecomposable representation other than SI. Sorry, let me go back. If I take an indecomposable representation other than SI and apply a reflection functor at vertex I to it, what happens to the dimension vector? It becomes precisely sigma I applied to the dimension vector. So the fact that I can take a dimension vector of an indecomposable representation and somehow keep applying sigma i's to it until I get a negative vector, until I get something which has negative components. This is going to be crucial because we will be able to then say precisely when this happens and just unwind everything back. So we are going to play reflection functors which act on indecomposable representations, and these simple reflections sigma I which act on vectors in Zn. We are going to play them against each other in a very nice way so that with this key fact, Gabriel's theorem, this part of Gabriel's theorem, the theorem that we stated today, this theorem will just fall out. Okay, so we are out of time. Let's stop now.